Hello, so today we are going to look at QuickSort, which is a sorting algorithm. It's a classical sorting algorithm, and it uses a specific approach called divide and conquer. So, for example, with an array like this, with the indices 0 here and 7 here, we can choose the pivot to be any element of the array. So let's say I choose the pivot to be the first element, which is 52 here. Then what I can do is just divide the array by that pivot, so that on the left side we have the elements smaller than the pivot, on the right side we have the elements bigger than the pivot, and then now we have two subarrays that we can just recursively sort using the same algorithm, QuickSort again. And so every time we'll keep dividing the array to two halves until we end up with one element, and then at that point we have a sorted array, right? And so what this will look like if I choose this here as the pivot, well, I will take all the elements smaller than 52, I will put them to the left. So what that means is that 41 is smaller, so put it to the left. 20 here is smaller, so we put it to the left too. And then 50 is smaller also, and 97 is not, so we put it on the right. 93 is bigger, so here we have 52, and then the elements bigger than it, which are 56, 56, 97, and 93. And this step here, where we took the pivot, we put it in the middle, and we put all the elements smaller than the pivot to the left here, so these are smaller than 52, and all the elements bigger than 52 to the right. And we can also, if the array contains duplicates, we can decide on which side to put them. We could put them on the right, on the left. We could decide that it doesn't, both are fine, right? And so this here is the partition step. And then the divide that we are going to do is that we are going to recursively sort the two subarrays. So 52 is already in the right position, but the two left and right subarrays contains elements that are not sorted yet. And so what we'll do is call a QuickSort on this portion here. So to do that, we can just pass the boundaries, right, like low and high here. And then we QuickSort also this portion. And since we are doing it in place, we don't need any combine step like we do in merge sort, because here we are just swapping and sorting in place, and so we'll end up with a sorted array. So the most important step in this algorithm here is the partition step, right? And so what that means is that, so the other recursive call is just passing the boundaries, right? So it's pretty straightforward. The partition step, though, is where we have different approaches that we are going to look at, and each of them has different characteristics and different time complexity and space time complexity mostly. And so here for the partition step, we have two known schemes. They are called schemes that we can use here. One of them is called the Lomuto partition scheme. Lomuto, like this. And then the other one is Hor's partition scheme. And so we are going to look at both and see the performance characteristics of each. So first, let's take a look at this one. Okay, so now let's take a look at this Lomuto's partitioning scheme, where we choose a pivot and then put the elements smaller than it to the left and bigger than it to the right. So here I have this array with these elements. It's an unsorted array. And so I'm going to pick the pivot to be the high element here, the element at the last position. We can also pick the first element. Both will give us the desired result, but let's just, for the sake of example here, take the element at position high as the pivot. And so the way to do this is we are going to start start scanning through the array from the first position. And to do that, we are going to use this j variable to scan the array. And then whenever we encounter an element that is smaller than the pivot, we will swap it with the I position and then increase the I value. We will see in a moment why this works. And so if I do this, so first I check, so my j variable will go from 0 until here, just before the pivot. And so the first thing I'm going to do is just check if. So the way I'm going to do this is I'm going to start my j pointer is going to go from the low element, which is the start here, to the high, which is here. So of course to high -1 because we don't wanna swap the pivot with itself. And then if we encounter an element at position j in the array, so that would be array j that is less than the pivot, what we are going to do is we are going to swap position I with j. And first I starts out as the start position. And so what this would mean here is that we will check 7 with 7, right? And so that's equal, so it's not smaller than, sorry, so we'll check 7 with 4. 7 is bigger than 4, so we don't have the condition. And so at this point we just move j to the next position. So j becomes here. And then here also, if we find an element smaller than the pivot, we will swap and then we'll increase I, right? Because we already used that element, right? So here with 8, we compare 8 with 4. 8 is bigger, so we continue increasing j here. And then 2 is smaller than 4, so now we have the condition that is valid. So at this point we swap I and j, which means we swap 7 and 2. So we'll do the swap here between 7 and 2. And so to do that, what we'll have is, I'm going to write it in green, so we would have 7 here, 2 here, and 7 here. And now, since we swap it, and because we find an element smaller than the pivot, we'll increase I. So I would advance. And then we compare, and j also would advance, right? Because we go to the next iteration of the loop. And so we have j here. And now we compare 6 with 4. It's bigger, so we just advance j. We don't do anything else. And then we compare 5 with 4, it's still bigger, so again we advance j. Now j is equal to 1, right? Which is smaller than 4, so we swap I and j, which means here we get 1 instead. And then instead of 1 we get 8. And we increase I, right? And now we increase j also because it's the next iteration of the loop. And then we compare 3 and the pivot. Pivot is 4, 3 is smaller, so we can swap I and j again. So we swap 7 and 3. So we'd have here 3 and here 7. And now we advance again I. And we advance to j. But now we will be done because j needs to stop at high -1, right? And so now we will notice something, which is all the elements to the left of I here are smaller than the pivot, and all those bigger than I, these are bigger than the pivot, right? This is what the whole, because whenever we found something that is smaller, we did swap it with I and advanced I. So anything to the left of I will end up being smaller than the pivot, and anything that wasn't swapped, which means it was bigger than the pivot, will be after I, right? And so here, now only thing left is to swap the element at the high position with the element at I position. Why do we do that? Because the structure that we want is that we want to have the element less than the pivot, and then have the pivot itself. and then have the elements bigger than the pivot after that, right? And so to achieve this structure, we need to swap this. So the last thing we do here after the end of the loop is we swap the element at index I with the one at index high, right? And so that will leave us with, here with 4. So we'd have 4 here, and we'll have 6, the high position here. And now we can recurse and do a quick sort on the elements to the left and on the element to the right, which means here that we will do a quick sort for this portion here and a quick sort for this portion here. And the 4 is already in its correct position, right? So we will continue doing the same thing for 2, 1, 3 until we end up with 1, 2, 3, and we'll continue doing the same thing for 5, 8, 7, 6 until we get 5, 6, 7, 8, right? And that's pretty much it, right? So we would what this means is that we will do quick sort again, starting for the same array, but starting from position 0 and ending at position 2 this time, right? Because we wanted to sort only this portion. And here we will sort at starting at position 4 and ending at position 7, right? And that's pretty much the essence of this partition scheme, is that we choose the pivot to be the last or the first element, and then we scan the array from start to finish, and every time we find an element smaller than the pivot, we swap it with the value, with the position I. Basically, I represents the boundaries between the smaller and the bigger portion, bigger than the pivot, of course. And so if we kind of write this in pseudocode here, what we will get is that we would have our quicksort algorithm here that we do on an array here, and of course we start out with low as 0 and high as the length of the array, -1, of course, the last position, right? And then what we will do is, while we continue until both indices meet, which means when they meet, we have only one element, and that element is by definition sorted, right? But as long as they didn't meet, we can continue recursing and sorting the subarrays, right? And so here we use the partition step, which we'll be using the partition scheme for here, to get us the partition index, which will give us, in this example, the position for this element. And so that would be partition for array and low and high. And then once we do that, we will do what we said here, which is quick sorting the left half and then the right half. So what does quick sorting the left half mean? It means calling quicksort, and the first element is still the same, it's still low, right? But the last element now is, so if this is p here, then it's just the element before it, so it's p minus 1, and this is p plus 1. So it's until p minus 1, and the second quicksort is called on starting from p plus 1 until the end, which is high. So what we would have here is p plus 1, and the end would be high. And so this is the template this is the quicksort algorithm itself, but we need to define partition, right? And so to do that, and here also the base case is when both elements meet, where we won't do anything and we'll stop there, right? And so here for the partition, let's define it. Here, this is where we will be using the Lomuto's partition scheme. And so we'll have partition for the array. So first we will pick the pivot to be the element at position high, right? So that would mean we'll pick this element high here. And then we will start, as I said here, we will scan from the start. So we'll put our I index to be low. And then we will start scanning using pointer j, which will go from low to high -1. And So this is low, of course. And then whenever we encounter, so it's the exact same thing we applied here. So whenever we encounter an element at position j that is smaller than the pivot, we swap aj and the element at position I, right? That's what we did here, right? Because we want the element smaller than the pivot to be to the left of the pivot index, which at this moment we are tracking with the index I. So we'll swap aj and ai, and then we will advance the I pointer, right? And now when we are done with the loop, that means we are at the position P of the partition, or position I contains the first element that is bigger than the pivot. And so we want to replace that with the pivot value, so that the pivot can partition the array into two portions smaller than it and bigger than it, right? So what that means is we will swap the element at the pivot itself, which is a high, right? That's what we chose it to be, and then we will swap it with the element as position I, of course, right? And that's pretty much it for the partition step using Lomuto's scheme here. And so let's type this using Python and run it on an example here. Okay, so here I just have the same example that we just saw in the overview. I've just written it in Python, and so here I have the partition step, and here I have the QuickSort algorithm. So same thing here, we just partition, we get the partition index, we QuickSort the left half, and then we QuickSort on the right half. And we start out with the entire array. And then here, the partition step, we choose the pivot to be the last element of the array, and then we scan, and whenever we find something smaller than the pivot, we put it to the left, and those bigger than the pivot, we leave them as where they are, so that at the end they will be all to the right of the pivot. And at the end, when we finish this scan here, we swap the element at position I, which is basically just after all the elements smaller than the pivot, and we swap that with the pivot element, so that the pivot element can kind of separate the elements smaller than it and the elements bigger than it. And that's pretty much all there is to it. And so let's run this on an example here. So I have here an unsorted array. So if I run it, we can see the array is sorted. Yeah, so that's pretty much it. So next we'll take a look at the second partition scheme variant, which is Hoare's partition scheme. Okay, so now let's take a look at Hoare's partition scheme. So this is the original partitioning algorithm created by Hoare's, and it's a little bit different than Lomuto's more common Lomuto's partitioning scheme. So this partition algorithm here works in a way where we have two indices or two pointers, one at the start and another one at the end of the array. And then we keep moving both pointers towards each other until we detect an inversion, which means basically we detect on one side a pair of elements where on the lower pointer side, one is greater than or equal to the pivot, and on the the end pointer side, it's lesser. Or equal. Like the handling of equals, we can either decide to make it on the left pointer or on the right pointer. And so these two inversions that we detect, or pair of elements that constitute an inversion, they are in the wrong order, and so we swap them to get the right order. And then we keep doing this until both indices at the start and at the end, let's call them I and j, until they meet or they cross each other. At that point, we are done, and the partition is done. So that's how it works. Now let's just take a look at how this would look like in an example like this one. So the choice of the pivot can be anywhere. We can choose the first, the last, or even a random position. So what I'm choosing right now is the middle element. So let's see how would executing that on this middle element work. So the first thing we'll do is we will take two pointers, one at the start and another one at the end. So what that would mean is that we would have I here at the start and j here, right? And so we'll check, we will keep advancing. So what we will do is basically we will have I and j. Let's just write that on the side, where I is the start position, right, which is low. So for the first iteration, low is equal to 0, but after that, since we'll be sorting subarrays, low may change, right? For example, for the right side, it may be 4, for example, or something like that. And so for j, it's the element it starts out at the last position, and we will iterate forever until the two indices I and j cross each other. And so I will do an if here to check if they crossed each other, which means they either met or one of them is j is now before I, right? If that's the case, then we are done. So we return just the partition index. We will choose that to be j, but the most important part is here is while the element is still in the right order, we will just keep increasing or decreasing the index, increasing for I so that we advance, and for j we decrease so that we advance on the right direction, right? And then here, so we will check while AI is smaller than the pivot. So that's correct, right? Because I is on the left of the pivot. And so if the element is smaller, that's exactly what we want. We want all the elements smaller than the pivot on the left and all the element bigger than the pivot on the right. So this is the correct order. So that means that let's just not worry about it. Let's just keep advancing I because that's the correct behavior. Now for j, we are going to check while aj is bigger than the pivot, right? So for the element on the right of the pivot, if it's bigger, then it is in the right position, right? And so if it is, then we just decrease j because it's already in the right position. But once we get here, what does that mean? That means that the two indices haven't been met yet, and the element at position I is bigger or equal to the pivot, and the element at position j is less than the pivot, right? Which means both are not in the right order. So if we swap them, we'll get them in the right order. We'll get the element at position I to be smaller than or equal than the pivot, and we get the element at position j to be bigger or equal than the pivot. So here we can swap A and j, and in Python swapping them, we can do that with just something like this. So all this does is swap at A with at j, with the element at position j. And once we do this, we need to advance our pointers, right? Because now these two are in the right position. So advancing I means going this direction. Advancing j means going on this direction. So that would mean j minus 1. Okay, so now let's try this algorithm here on this example. This is the partition algorithm that we are going to apply. And so 7 is, so for this loop, 7 is smaller than the pivot, which is 6. Sorry, 7 is not smaller than the pivot, it's bigger. So we exit the loop here, and we come to this here where aj is bigger than the pivot. So what that means, so we check aj. What is aj? It's 4. 4 is smaller than the pivot, right? So we exit this one too, right? And so here we check, is 0 bigger or equal than 7? No. So that means we are here at the swap iteration, and so we swap 7 and 4. So what this means is we get 4 here, and we get 7 here. And now we advance both pointers. So I becomes here, and j becomes here. And now we go to the next iteration. So we check, is AI less than the pivot? Is 8 less than 6? No. So again, we are here with I equal to 1. And then we check for j, at position j, which is 3. Is it bigger than the pivot? It's not. So it is also out of place, right? So here, so that means we get here also with j equal to 3, j equal to 6, right? And so 1 and 6, they didn't cross each other yet, so that means we swap both. And so we swap the element at position 1 with the element at position 6. So we'll swap 8 and 3 here. So here we would get 8 and here we get 3, and we advance our I pointer here. And J also advances. And now we go again. So is AI smaller than the pivot? So AI is 2. It is smaller than the pivot, so that's good. So we just advance the pointer. So I is here. So we check again. Is AI smaller than pivot? So 6 smaller than 6? No. It's equal. So we exit the loop. And so now we are at this position here with I equal to 3. And then we check, is AJ bigger than the pivot? AJ is 1. Is it bigger than 6? No. And so we exit again here with J equal to 5. So 3 is still smaller than 5. So the 2 pointers haven't crossed each other yet. And so we come at the swap iteration. And so now we swap 6 and 1. So we swap 6 and 1. And we advance the pointer again. So I becomes here. And J also advances. So now J is here. And now we go again and we check. So is AI smaller than the pivot? So the pivot is now just remember what we will do here is we will put pivot at the start here, because it may get replaced. So what we are going to do is we are going to initialize pivot here to position mid, right? And that we can do with high minus low divided by 2 plus low. Or we could also do high plus low divided by 2. But this is just safer. And so now our pivot, we know that the value of our pivot is equal to the original one, 6. Right? So this is our pivot. So is AI smaller than the pivot? So is 5 smaller than so is 5 smaller than 6? So we check, is AI, which is 5, is it smaller than 6? It is. So we advance to the I pointer here. So I becomes here. And AJ is 5. Is it bigger than 6? No. So we exit the loop. So at this position here, we have I equal to, so I equal to 5 and J equal to 4. So you can see now they cross each other, right? Because now J is smaller than I, and so we return J. So that means we return J, which is equal to 4. So that would be the partition index. Now, what can we say about what's on the left of the partition index and what's on the right of the partition index? So all the items on the left of the partition pointer plus the item at that position itself, those are smaller than the pivot, and all those to the right are bigger than the pivot, because, so you can see here, the partition pointer is this. So all of this is smaller than the pivot. And all of the right portion here is bigger or equal to the pivot. As you can see here with 6, 8, 7, those are bigger or equal to 6, and those are smaller than 6. And so this is how, for the whole partition algorithm, it's different than Lomuto's, because Lomuto's puts the elements in the correct position, but all those to the left of it, excluding the partition element, are smaller than the pivot, and all those to the right, excluding the partition index, are bigger than it. But here, all those to the left of the partition index, including the partition index, are smaller than the pivot, and all of those to the right are bigger or equal to the pivot. And so now we can just quicksort on those two halves, and we will be done, right? So what this means is, what will be the boundaries of both quicksorts? So for the first one, it will recurse on, of course, the start position, which is low, and this is, let's call it P, the partition index, until P, because the partition element position is included in those smaller than the pivot. And it will quicksort for the right side on p+1, which is what we are doing here. This is p+1 until the end, which is high position. And so we will do these two quicksorts. And this is the partition step. Yeah, so that's pretty much it for this algorithm. So let's implement it like in the entirety of the algorithm in Python and run it on an example. Okay, so now let's see an example here. So the start of the we launch our quicksort on the first position and the last position, right? And then we continue until both pointers meet, right? And we get the partition index. Then we sort the left half and we sort the right half, right? So this is the same in both partition schemes, right? Except here we sort excluding the pointer, but here we sort including the pointer, right? Now here in the partition step, we take the middle element as the pivot. We can take maybe low or high, both work fine, or even a random element. And then we put our two pointers, one at the start of the array and the other one at the end. And while the element is still smaller than the pivot, which means it's in the right position, we just keep advancing until we find an element that is no longer in the right position because it's bigger or equal to the pivot, and those to the left have to be smaller than the pivot, so it's not in its right position. So we exit this loop and keep track of it in the position I, and then for j, we traverse from the right because all those to the right have to be bigger than the pivot. And so whenever we find one that is smaller than the pivot, that means it's not in the right position. So when we are here, we have two elements I and j that are not in the right position. And so we can swap them, and by swapping them, we make them in the right position because the element at j, we exit the while loop because it was smaller than the pivot, so it belongs on the left side. And here we exit because it's bigger than the pivot, so it should be on the right side, right? So by swapping them, we make it on the right side, which is the right thing to do. And then we advance both pointers. And this is just so that when both pointers cross each other, which means we have processed the entire array because we processed the right portion in the left portion, so we can exit at that point, and the pivot index is j. And that's pretty much it for this. And so I'm going to run it on this unsorted array. And we should get 1, 2, 3, 4, 5, 6, 7, 8, right? So let's just run it here. And now we have a sorted array. Yeah, so that's it for this different partition scheme. Now let's take a look at the time complexity of both solutions, or of quicksort in general. So for both partitions, if we take a look at the algorithm here, so for example, for the Lomuto's partition scheme here, we do only this loop, right? In terms of time complexity, we do this loop, which is O of n time, right? We go from j from low to high, and that's the main loop we are doing here, so it's O of n time. And if we take a look at the horse partition scheme, it's also similar in that, well, we have two pointers, I and j, and I increases always and j decreases on each iteration, right? So either because of this, or maybe because of this or this. So at least for each iteration, we will have both I increasing by 1 and j decreasing by 1. And so what this means is that in O of n time, both pointers will have met and we will return j. And so here, this means is that the partition step here is also O of n. So we definitely know that the partition step takes O of n time. Now for the quicksort algorithm in general here, so the template we are doing for our solution is this. So we call quicksort, right, with a low and high value, and then before the two pointers meet, we do the partition step, which we said in both cases it's O of n, and then we call quicksort on the left half and on the right half. Only these pointers change between both solutions, but they change just by 1, so it doesn't really matter for our analysis here. but we call this on half the elements of the original problem size, right? So this would mean if we consider n to be the problem size here, the number of elements that we are dealing with, then we will call this with n divide. Let's just take this notation to be the time complexity here. So what this means is that we'll do T of n divided by 2 here, right? And we will do n divided by 2 here. So in general, this follows the structure of calling an original problem and then creating two subproblems where each is of size n divided by b, where here we have b equal to 2. And then we recursively call it, and then we combine the result. Here in the combined step, we are doing nothing because we are sorting in place, we are swapping in place, so the combined step is O of 1. And here what this means is that if we kind of write this in terms of time complexity, what this means is, so just one distinction to note though is that n divided by 2 is only in the best case, right? Because in the best case, we will end up choosing a pivot that is really good in that its left size is half the size and its right size is half the size. So what this means is that if we kind of just look at the best case scenario, not the average case, not the worst case. So let's just look at our best case. So in our best case, we'll divide problem size by half. So what this means is that let's call it C, or maybe let's call it T, right? So what this means is our T of n would be, we are calling it twice, right? Two calls, QuickSort on this one. So it would be 2, and each of them is of size n divided by 2. And here we do the partition step once, right? Once per call, which is n here, right? So what this means is it's plus n. So this is for the partition, and this is the subproblems. And this here is a recurrence relation that is solvable by the master theorem. I'm not going to go into details about like the 3 different cases of it, but this specific case is of the form T of n equal to a multiplied by T of n divided by b plus some function of n, right? So this is the general form, and this form of the master theorem, it's case 2. If we look at it, and it has automatically, when you have something of this form, applying that theorem tells us that the solution is O of n to the power of log b of a and log of n multiplied by log of n, right? So in our case here, b is equal to 2 and a is equal to 2. And so if we plug these values into what the master theorem says, we will get O of n log base 2 of 2 log of n. And log base 2 of 2 is just 1, so what this means is we get O of n log n. So this is our time complexity here of QuickSort. And generally, since the lower bound for comparison sort algorithms, for all sort algorithms that use the comparison as the main construct, the lower bound is O of n log n. So what this means is that QuickSort is close to optimal here. Now, in terms of space complexity here, so the main thing that will take space here is these recursive calls on the stack, right? Because the partition step doesn't really use much space because we do the partition in place, right? So what this means is mostly what we'll be using is the stack space here to do the 2 recursive calls, right? And so each step we divide the problem size by 2, right? So we'll keep dividing the problem size by 2 until we have only one element array. So what this means is that the number of recursive calls would reach, so we will end to 1 after log of n calls, right? And so what we can deduce is we'll do log of n calls to the subproblems here. So what this means is our space complexity would be just O of n log n. Sorry, O of log n, right? And so here, we know that on average, both our time complexity is of n log n, and our space complexity is of log n. Okay, so now we looked at the average time complexity here, right? But how can this degrade? What is the worst case complexity here? So let's say we have a sorted array, right? So let's say we have an array that is 1, 2, 3, 4, 5, 6, 7, 8. That is already sorted. And let's say we pick the pivot to be the first element. Whether we are using the Lomuto's partition or Hor's partition, it doesn't really matter. Both will get the same worst case. But here, let's say I'm just using the Lomuto partition. So I would choose this as the pivot. So what this would mean is that I will recurse on this as the left side, since this is smaller than the... let's say if it's equal, I will put it on the left side, right? So let's say this is smaller or equal to the pivot, and this is bigger than the pivot. So we will recurse on these, and then we'll recurse on 2, 3, 4, 5 until 8, right? So this means we'll choose the pivot to be 2 again, and we would have the left side be like this. This is smaller than the pivot, and we'd have the right side be this portion, bigger than the pivot. And we'll keep doing this as we go down. So here, choose 3 as the pivot for this portion, and then we would have this, and we would have this also. And so if we look at the time complexity for this, let's say n is the length of the array, what will happen is that we are not dividing the problem size by 2, we are just decreasing it every time by 1. And so what this means is the overall time complexity in the worst case here. So the first time we will do n comparisons, right? So we will do n, and then we will just reduce the problem size by 1. So it would be plus n minus 1, and then we'll reduce it by 1 again, so n minus 2, and we'll keep doing this until we reach maybe 2 or 3, right? And so what this means is this is just a summation where the result is n plus, well, the result is n plus 1 multiplied by n plus 2 divided by 2. So the time complexity may be minus 3 here because we don't reach 1, right? And then this overall is n squared plus n plus 2n plus 1, but the dominant term here is n squared, right? So this is O of n squared. So in worst case, quicksort time complexity can get to n squared, O of n squared, which can happen if we have a sorted array and we pick the first element as the pivot. It can also happen if we have an array that is sorted in decreasing order and we pick the last element as the pivot, right? And so with some configuration where and choosing and some selection of a pivot, we can end up with O of n squared time complexity. This is just something to be aware of. We can avoid this for quicksort by, for example, shuffling the elements before applying quicksort. That way we are sure we don't get this specific case. Yeah, but this is something to be aware of. Yeah, so that's it for this quicksort, I think. Thanks for watching and see you next time.